And you'd have to lean over to the wall.
All right, so in choosing the correct confidence interval, I'm going to create a flow chart here. And my suggestion, I'm not gonna put this anywhere for you to download, so you're gonna write this down. We're going to ask several questions that are going to lead us to whether we use the z-test, or z distribution, or the t distribution. Okay, I interchange these words. You'll hear me say on accident z-test or t-test, and that's in regards to what we're going to do with hypothesis testing in a few weeks. Basically with like hypothesis testing, what happens is you make a hypothesis. Okay, you as the researcher, you make a decision and say, I think that this is the relationship between X and Y. And then we collect the data, we process the data, we determine these statistics, and we let the data then decide whether we accept that hypothesis or we reject it. The things that we go through, the procedures that we go through to say that we accept it or reject it is called hypothesis testing, and we use z-test and t-test to do that. So I might accidentally interchange those words. It's really not a big deal, but that's kind of where we're at. So first thing we're going to do is ask the question, what type of data? Okay, so this chart that I've created here is, like, this is it in full scale. So it's kind of lengthy, so you might want to give yourself a little bit of room. Center this. So the first thing you're going to ask is the question, what type of data? And there's going to be two answers to that. We're going to talk about means, which is obviously our mu. Or we might talk, and there's some things on this chart that we haven't talked about that we will get to, or that we haven't talked about and we might get to. Okay? So one of those is proportions. We will talk about proportions. Population proportions, very easy. You probably already understand the concept of it. But that's maybe towards the end of next week, beginning of the following week. So if I'm going to concentrate right now on this means side. So recognize that that's what they're asking us for. Find confidence interval for a mean or for mu or whatever, however they phrase it. The next question we're going to ask, is our sample size bigger than or equal to 30? Central limit theorem stuff, right? Okay. Because if it's bigger than or equal to 30, it guarantees normality. The distribution becomes normal. And when it becomes normal, then we can either use the z-test or eventually the t-test. Okay. So if it's greater than 30, we're going to have obviously a yes or a no to that. So when I say yes, so I say yes to that. The next question is, do you know the population standard deviation? Okay. Is the population standard deviation known? Okay. And that's sigma, right? A lot of the problems that we do, it won't use the symbol sigma. You go through your homework, 8.1, 8.2. It's very rarely using that symbol. It's saying the words population standard deviation is yada, yada, yada. Okay? So if we know that, this was 8.1. So if the answer to this is yes, if the answer to that is yes, we can use the z distribution. If the answer to that was no, okay, if the answer to that is no, we're going to use the t-distribution. Okay, and if I'm going to use the t-distribution, that means I must be able to find the sample standard deviation. That's the thing that will take place of sigma that is used in the z distribution. Okay, we're going to write the formulas here in a moment as well to make comparisons of the formulas for the z and t distributions for estimating the mean. So if I'm going through a problem, they say, hey, you're looking at means. You've got a sample that's bigger than 30, but you don't know the population standard deviation. Well, then I can come down here and I'll use the t-distribution. Okay? If they say I do know the sample, or the population standard deviation, then I can use the z-distribution. Is that okay with everybody? Okay. So here, so let's talk about the two distributions. So the z distribution, that interval, confidence interval, is going to be found by taking x bar minus z sub alpha over 2 times sigma over root n is less than mu is less than x bar plus z sub alpha over 2 times sigma over root n. Okay, that was what we talked about in 8.1. In 8.2, it's the t-distribution. Okay, if I use the t-distribution, it's x bar minus t sub alpha over 2 s divided by root n less than mu less than x bar plus t sub alpha over 2 times s divided by root n. Okay, so my hope is that you see that if you know the population standard deviation, you're going to use the population standard deviation in the formula. Okay, and if n was bigger than 30, we know that this thing was normal, or that the central limit theorem provides normality, so we can use the z distribution. Okay? Now, if we still have something that's bigger than 30, but we don't know the population standard deviation, well, if you don't know the population standard deviation, you don't know that thing right there and right there, then in order to develop a confidence interval, the only thing that you can replace the population standard deviation with is a sample standard deviation. It'd be your best replacement. Does that make sense? Okay. If I don't know the mean, or sorry, the standard deviation of the population of students in this class and their mean age, then maybe taking a small group of those students and finding their standard deviation would be the best estimate for the population standard deviation. Does that kind of make sense? So that is why we would then, if I don't know sigma, we would come down here to the t-test or t-distribution, and we now can replace sigma with s, so that's the sample standard deviation. And when we use the sample standard deviation, we have to use a t-value, okay, because it's a family of curves now instead of just the normal standardized curve. Okay, so my hope is that we see that this blue formula and this red formula are really the same thing. Okay, it's x bar minus some value. Okay, and how we garner that value is different depending on whether it's normal or if the central limit theorem is existing or not, and whether I know sigma or if I know the sample standard deviation. But those are the only things that change there. Okay. Yes. So, in the what do you mean in the homework they're easy? Are they writing it this way?
They don't write it anyway. It's just learn how to do it.
Well, I mean, you gotta.
Well, no, I do like that part and then it's subtracted or whatever. It's not like.
Yeah. So a lot of times they'll write it this way. They'll say because this here is our error, okay, which allows the creation. You take your point estimate and you subtract your error, add your error. So a lot of times they'll say error is either the z or t, depending on which one you're using, over root n. And then they'll say, well, x bar minus e less than mu less than x bar plus e. And then you write it as interval notation. So it's really x bar minus e comma x bar plus e, which is a little bit easier, okay? But not all of you have had college algebra and have talked about how we take something that is in what we call here set builder notation, and this is called interval notation. It's just, but yes, I would agree that maybe the way we see it in the homework and the way we see it traditionally notes is a little bit different. If we were to answer this question up here as no, okay, we're going to want to know, is the population normal? So if we have maybe a situation where we cannot get a sample big enough to where the central limit theorem would kick in, we would want to know, does the population that this sample of maybe 10 or 15 or 20 or whatever, is that coming from a population that is normally distributed? Because if it's coming from a population that's normally distributed, then the sample will be normally distributed. Does that make sense? Okay. And if that's the case, so let's say, so this is going to get a little bit lengthier here. Let me get this stuff moved. I'm sorry, did you write that stuff there? Sorry. So this is going to come down. So we're going to have a yes or a no to this.
This is why I don't take notes. I'm too afraid to take notes.
All right, so we're going to ask the same thing that we asked up here. Okay. So if we said yes, that the population is normally distributed, well, do you know sigma? If I know sigma, you could. If you know sigma, you're going to use a z distribution. If you don't know sigma, you're going to use a t distribution. Okay? So as we go through this, I know this is maybe a lengthy kind of chart here, but what is the main piece of criteria that we have to have for us to use the z distribution? You have to have the population standard deviation. You have to have sigma. Okay? And if we look at this, even though they give me that criteria that n has to be greater or equal to 30, okay? The n being greater or equal to 30 guarantees that we can have normality, okay? But it doesn't mean that if you're less than 30, if I've only got a sample of like 10, it doesn't mean that sample of 10 is not normal. Does that make sense? Okay? It's just not guaranteed. But if the population that those 10 things came from is normal, then that sample is normal, okay? And we can use the z distribution as long as we know sigma. If we don't know sigma, then we got to use the t distribution, okay? Now, this next part, coming off of this up here, okay, so because there's a no here, right? We asked the question, and I'm going to do this in red because we might not get to this. Yeah, and that's only that's not that's like it's like this size right here. So population normally distributed. If the answer to that is no, and here's my question: how many distributions have we talked about so far that were not normally distributed? Really not. We talked about the binomial distribution, which we then talked about how that segues into the normal distribution. But if we answer no to this, what we're going to ask eventually, and this is the thing about statistics, this is the thing really about any high school math course that we take. And even though this is like, some of you taking this college credit, it's like, I don't know if I have the textbook, it's called elementary statistics. Some classes or some places call it introductory statistics, okay? So we're just like scraping the surface of a lot of different concepts, right? Okay, so we could get a lot deeper, and my hope is that at some point, once we get finalized with all of the things that are required through roads, and we get that information covered, we can go back and kind of talk about these things that we didn't dig into as far as what I think we should, okay? And this would be one of those things. So we'll ask, is the population large? Okay, and that's a pretty ambiguous question. Okay, so we'll have some criteria that allows us to determine, based on our information, our values that we have, of whether the population was large or not. Okay, we'll be able to definitively tell that. Okay, so if it was large, what we would use is a binomial distribution. Okay, and we'll talk eventually about what a binomial distribution, in regards to like a binomial test and all that kind of stuff, deals with. But that links back to what we talked about previously. In proportions, when we talk about proportions in the next couple of weeks, that is essentially a binomial distribution as well. Remember, binomial means two, so you basically have a success and a failure. You guys remember talking about that? Fixed number of trials, probability of success is consistent or the same all the way through for every trial. So that's kind of what we target here if the population was not normally distributed and we had a large population. If we had a small population, then what we would use is this distribution called hypergeometric. So hypergeometric distribution. Okay, and a hypergeometric distribution is more like the situation where, if I want to know like the probability that maybe we're looking at like eye color, okay, and my options for eye color are blue and brown. Okay, that's binomial. It's like I give you two options. Maybe a blue would be a success and a brown would be failure. Okay, but if I wanted to look at a situation where my choices were blue, brown, green, hazel, whatever, I got more options than just two. That's hypergeometric. Okay, and we would talk about those probabilities using that type of distribution. Okay. Wrote it in red. We might not get to it. Okay, we'll just see. All right, so now going up to, and we could do this next week or when we get to it, but might as well do it now since we're here. This link right here, this branch, and if you run out of room or whatever, it doesn't have, you can do it this way. Okay, it doesn't matter. Just as long as you've got a branch coming off this and you can talk about proportions.
I said scroll down.
What?
I said scroll down in all caps, so I know to scroll down.
Usually scroll down means scroll down.
Yeah, that's how beautiful.
You want me to scroll down? Oh, you're just talking about yourself?
Yeah.
All right,
She wrote it for herself.
good deal.
Yeah. I'm taking notes for him. Someone encouraged me.
All right, so proportions.
Thank you. So,
Okay, so what this is basically saying is if we take this class as a population and we say that 10% of them are left-handed, could we take how many there are in here? Let's say that there's 20 in here, and then multiply that 20 by 10%, and we would tell us that 2 out of the population are left-handed. Right? That's proportions. Okay, that's very easy. Okay? We'll talk later on why we would use this and all that kind of stuff. But there are some conditions that need to be met in order for us to actually realize that our calculations model the population, okay? First thing is that N times P has to be greater than or equal. We're gonna say 5. Some textbooks say 10. We're gonna say 5. And N is just the sample size, and P is the probability of a success. Maybe P is being left-handed, okay? So if that situation that I just explained was 20 of us in here, multiplied by 10%, we get 2, okay? That 2 is not greater than or equal to 5, right? So because it's not greater than or equal to 5, there are not conditions met for us to use proportions, okay, and determine intervals with those. We also want N times Q to be greater than or equal to 5. Q is the complement. So this would be, we talked about what's the probability of being left-handed. So the complement, N times Q, would be the probability of being right-handed, right? Or the proportion of students or people in the population that were right-handed. So there we would take 20 times 0.9, and we get 18, right? Okay. That would be, well, we would satisfy, obviously, 18 is greater than or equal to 5, but we need to satisfy both those things for proportions to exist. And again, I was writing that down, but I want you to kind of understand what does it mean when we get to it in class later on in the week, next week, week after that. We'll talk more about it. But if that's the case, if you have both these conditions met, that means things are normal, and we can use a z distribution. If it's not normal, then we're going to ask a question about whether the population is large. And if the population is large, we can use the binomial. If the population is not large, we can use the hypergeometric. That's right, hypergeo right there. And again, probably should have done this in red. We probably won't get many questions early on, if not until like maybe at the end of the year when we backtrack and say, okay, now we've talked about this stuff that we've laid out, we had to get covered. Now we might come back and talk about that stuff that's highlighted. Okay. So as we go through, we're going to have multiple intervals. Okay, intervals for means using the z distribution and t distribution, and an interval used for proportions. Okay. All three of those things use either the t table or the z table. Okay. Basically, what happens is if you know sigma, which is the population standard deviation, you can use the z distribution. If you don't know sigma, you're going to have to use the t distribution. That's basically what it all boils down to. Okay. Now we like to have the acknowledgement that our sample is bigger than 30 because that's automatically then going to tell me things are normal, and we can use the z distribution. But this is still right there, regardless of the sample size. That's critical to decide which distribution to use. Okay, now, that's kind of, and this is like all statistics, what happens is when we are a researcher, and we create, like we want to see if there's a relation, basically think about what researchers do is they take these variables and say, okay, is there a relationship between these variables? Okay, we've got a person that's ill, we've got this medication, the variable, we give it to the person that's ill, do they correlate? Do they impact one another, right? Okay, so when we do that and we're collecting this data, we got to be thinking all the time about a chart like this, but it's probably much, much larger than this. Thinking about, okay, what kind of data do we have? What are we trying to measure? What's the relationship we're trying to measure? And then that will kind of filter us down and say, okay, you have to use a z-test here to maybe accept or reject your null hypothesis. Or maybe you got to use a z-test, or maybe you've got to use a p-test, or maybe you've got to use a binomial test. Okay? There's always a constant thought flow chart type thing going on because the problem when it initiates as humans, and the problem initiates, we do not know, or the problem that arises isn't going to say, hey, I'm a Z distribution, or hey, I'm a T distribution. It's the information that you're able to garner to create process that's going to tell you then to use one of those appropriate measures. Does that make sense? Okay. I kind of compare it to, if I'm solving equations and I maybe solving proportions and I cross multiply and I get the largest variable to be x to the first. I'm going to solve that like a linear equation because that's exactly what it is. But if I cross multiply and I get x squared, now what do I have to do if I'm going to solve for x? Let's say I have x squared and I have x to the first also in that equation. Don't you factor? But that trinomial that pops up doesn't say, hey, remember me? You got to factor me. Okay, you got to get everything equal to 0 and do that kind of stuff. Or if I get x squared and I don't get an x to the first when I do cross multiplying, it doesn't pop out to say, hey, you can use the square root method on me. Just isolate the x squared and then square root. There's a lot of stuff in mathematics that when things are generated, there are implied procedures that then take place after that. They're not explicit. Does that make sense? I wish every problem, as you were working on it and something new came up, it came with instructions. Because then everybody could do the math, right? It doesn't work that way. I think, though, this might be something that, as we're working through homework, might be of benefit to have beside us. Might help us target the correct distribution. In the 8.1 and 8.2 assignment, they're towards the end. There's a couple in there. I don't like the wording. Kind of came across it this morning. Not everybody, I don't think, got the same exact problem. But some of the wording is confusing. And it doesn't really, I think, make a lot of sense until you read the whole thing. So what I mean by that is if we look at, I think it's like question 7. I think it was 6 and 8 maybe. And we'll talk about it in more detail. And I'm going to extend these assignments. Two is a we'll talk about it because it's a notation thing. So this one here, this is question 6, says in a random sample of 13 microwave ovens. Okay, so their N is less than 30, right? Okay, and it says the mean repair cost was 80 and the standard deviation was 1510. It says using the standard normal distribution with appropriate calculations for standard deviation that is known. Okay, so if you do this, the way I read this first sentence is that when they say and the standard deviation was $15.10, the way I interpret that, and this is all like English and comprehension, all that kind of stuff, the way I interpret that, I don't know, direct objects, whatever it is, I attach that 1510, and that standard deviation, is back to the sample. Does that make sense? They're not, as we continue to read, say using the standard normal distribution with the appropriate calculations for a standard deviation that is known, assume the population normal is zero, find the margin of error. They're saying that 1510 is sigma, population standard deviation. Yeah, that's the big one. Which I think that is maybe a little bit misleading. Okay? If you view it as sigma or if you view it as S, does it change that portion of the formula? Let's say, so that portion of the formula is whether it's either S over root N or sigma over root N. It's that value over root N, right? Okay. What becomes a problem is if I view that as the sample standard deviation, then I have to use the t-table to get that multiplier out front. If I view it as the population standard deviation, then I use the z-table to get that multiplier out front. And that's what we have to pay attention to. But as we continue to read, a 98% confidence interval using the t-distribution was this. Okay? So do I use the t-distribution with this information here?
Yeah.
It's just going to generate that again, isn't it?
That's fine.
So they want you to use the z-distribution here. So as you generate a different interval than that. And what's going to happen is that the interval, basically what they're trying to say here, when you do this problem, is that because you use the z-distribution, the interval is going to be narrower than that interval right there. But the key thing is that the mean, whatever the population mean is, these, by looking at the t-distribution and the z-distribution, these numbers are not going to differ very much. Does that make sense? So basically the argument is we can use the t-distribution to give us good estimates that we would normally garner with the z-distribution. Does that make sense? So the t-distribution, we can use that if we have small sample sizes, right? Okay. So if I only have, obviously there's less variability when we have larger sample sizes, but there might be, for whatever reason, maybe we got a rare disease that we're trying to analyze, and I can only get 15 people that have that disease. Well, if I'm trying to run statistical analysis on them, I can't use, because I don't know if that's normally distributed, right? But the t-test allows me to fix that. Does that kind of make sense? If we were to take, let's say this entire class, let's say this class had 50 people in it, and we were able to take and find your guys' actual, let's say, mean height. Let's go mean weight, okay? And then do a since I know the population, okay, I could do a z interval and find the 99 or 95, 97, whatever percent I want, confidence interval for where that mean should be. Does that make sense? For the population, okay? Now, the reason I maybe want to do that is because I have population at my disposal. So I can know exactly what the mean is, right? If I do that interval, that mean is going to fall inside there, right? Now, if I took that entire population, knowing that information, and then say, well, let's assume that we don't know that information. Even though it's sitting there in the background, we know it, let's kind of turn our eyes to it, turn our back to it. And I say, okay, I'm going to use maybe U25 people to estimate the mean of the population. In that case, I'd have to use the t-test, right? T-distribution. What that's going to allow us to see is that the interval for the t-distribution is very, very similar to the interval for the z-distribution. Basically, they're going to approximate each other, okay? But the z-distribution will always be narrower than what the t-distribution is. But the mean will still be in that interval. Does that make sense?
Okay, guys.
I wish we had, I don't want to create like fake data for you, but I wish we were in like a lecture hall where we had 100 people in the class and we could do something like that where we have the ability to say, this is our population. Let's find all this information that we know, all of these parameters of the population. And now let's see if we kind of ignore that. Even though we got it written down, we ignore it and say, okay, let's say we don't know that information. Let's take this sample of 30 people or 25 people and run through all the tests and analysis of those statistics of those 30 people and see how well those statistics of those 30 people match up to the true parameters of the population. And they're going to match up really well. Does that make sense? And that's what statistics is trying, that's what this question is trying to show us, is that we have statistical analysis procedures that even if we don't know everything we need to know, all the population stuff, we can work with the sample, and the sample is going to give us the information we need. It's going to be a very, very good estimate for the population. Okay? But I think this question could be fixed by simply adding maybe that this is the standard deviation of the population or sample, however they wanted you to view it, okay? But because they say they use the t-distribution here, by default, then you have to use the z-distribution here. Yes?
I don't know why you're so confused, man. 15.10 is the data that goes on top, 13 is the one that goes to the bottom.
It is. You're right. But the number in front of that, the z-score or the t-score, is going to be different. So you have to decide, based on that phrasing, which one of those is appropriate.
Yeah, the z-score. You said z-score. No, why are you so... All right.
This one,
I know, it's so hard, though.
okay, so this one, in one of the videos I explained when I was gone that some notation is different from text to text. We use this notation in our textbook in OpenStax. Some textbooks use Z sub C, where C is a confidence interval. So we want to be 85% confident here. Okay? So what that means to me is that we're looking for the Z scores where this central 85% resides. Okay? Well, then for us, so when they say Z 0.85 here, because that's what the C is, the way we've been thinking about it is that it should be Z sub 0.15 over 2, or z sub 0.075. Does that make sense? So then in my table, that's the number I'd be looking up in my table, or I'd be looking up 1 minus that in my table. Okay, so if I look up 0.075 in my z table, we might have to pick up here tomorrow if we run out of time. So I'm going to look up, so because it's smaller than 50%, I know it's going to be negative. So I'm just going to search through here and look for 0.075. So it's between these two. Okay, so negative 1.4. Which one of these is closer to 5? This one's closer, isn't it? Okay, so negative 1.44 would be that score that we're looking for. That's what I closed it, but that's what we'd be typing in. Does that make sense? Okay. And then it'd be positive 1.44 as this farther or further to the right z-score. Okay. We'll pick up with that tomorrow. We'll do another example of that simply because I closed it. But when they say z sub c in that question, we could view it as z, so we want alpha over 2. So basically what I did here is I took 1 minus the c divided by 2, and that is equivalent to your alpha over 2. So if you want to make that distinction. Does that kind of make sense? And that's the thing that I struggle with, and which is going to be the best to demonstrate to you. Do I show you just alpha over 2? Because then when you get into another area that uses statistics and they're using z sub c, do you really know what that means? Even though you've seen it, you just use it as a different notation. I want to show you both and use both. No new homework, but I'll keep everything open that was open.